cosmos, which essentially means order. It means order as opposed to chaos. So it means something that has a rational order. And logos, in fact, means word, but also knowledge. Okay, so cosmology, in some sense, is a way to put order in a rational way, in a way that is understandable, and in a way that encompasses reality as broadly, thought as we can. So everything that is around us, and so it is important to put what we do in perspective. So let me start by telling you a little bit about where in the cosmos, in the universe, our little planet is. And as you know, our planet is just one little rock that is orbiting around a big star called the Sun. As you know, there used to be one more planet that is no longer considered a planet, and my wife Tesla, in fact, has some responsibility in Pluto not being anymore a planet. This was decided in 2006 at a meeting of the International Astronomical Union. Now Pluto is just classified as a dwarf planet, and there's a couple more dwarf planets that have been identified as such. So our Sun is one little star in a galaxy called the Milky Way, and the Milky Way itself is one of about 100 billion galaxies that we know of in the universe that kind of look like the Milky Way. So, since there's about 100 billion suns in the Milky Way, this means that we live on a rock orbiting about 1 out of 10 to the 22, so 1 followed by 22 zeros, sun-like stars in the universe. And yet, it is clear to us from observation that all of the stars and planets that we observe in the universe, in the grand picture, are actually just a teeny detail of what the universe is made of. It's less than 1% of the matter and energy budget of the universe. So, cosmology, the knowledge of the order, is about making sense of all of this. And now that we know that that what we see is actually just a detail, we're going to go well beyond what ancient cosmologies we're dealing with, and we have models that are a little bit different from those that the Egyptians had, or those that folks in Europe in the Middle Ages had. And what we believe is the picture of the universe in modern cosmology is one that is dictated by observations of the grand structure of the universe and by extrapolations that are based on our knowledge of particle physics. So the way we think of the universe is in the context of a model called the hot Big Bang model, where the universe was increasingly hotter and denser as you go back in time. And the way in which we extrapolate is by our knowledge of the elementary constituents of the universe. So for example, at a time of about 10 to the minus 10 seconds after the Big Bang, so a very, very small time, the universe looked a lot like what we are exploring with the Large Hadron Collider that I believe some of my colleagues have told you about. This grand accelerator operating in Geneva, Switzerland. And as you go farther in time ahead, you cross, for example, the point where particles were behaving roughly in the way that they behave today. So you had atoms made of nuclei and electrons orbiting around nuclei. And then we care about how galaxies and stars formed and so on. And so different pieces of physics come into this picture at different points in time. And for those of you interested in particle physics and cosmology, the beauty of this is that in the very early universe, particle physics is the language that is relevant, is the way in which we understand how the universe looked like. So it is fair to say that we have a standard cosmological model that maps and predicts the universe in pretty much exactly the way it looks today. And we used to believe that the universe only contained matter, and if that was the case, after the explosion, after the original expansion of the universe, this expansion would be decelerating because matter has a gravitational pull, and so things would slowly collapse or be pulled together, and so the universe would be decelerating. But we know that this is not the case. So observation told us that, in fact, the universe has an accelerated expansion, and there's something that we don't know the nature of, called dark energy, that is pulling the universe apart at an accelerated rate. So not only do things get further and farther, they do that in an accelerated way, so in a way in which the velocity increases with time. Okay, and this dark energy, the discovery of dark energy was what was awarded the Nobel Prize last year to these three guys. And here's a picture of two of the teams, two of the leaders of the teams that discovered this. So this guy is Brian Schmidt, who's from the Australian National University, which was leading this high-Z supernova search team, and Sol Perlmutter, who's a colleague at the University of California, Berkeley, was leading the competing project, supernova cosmology project at Berkeley. So the picture we have of what's in the universe, as I said, is one where stars and everything we observe directly is a teeny detail, is a teeny slice of the pie of matter and energy. So this is the energy content of the universe. Most of the stuff that makes up the universe is this dark energy responsible for the accelerated expansion. And most of the matter, so most of the things that behave under gravity in the same way as ordinary matter, is made of dark matter. So this big chunk of the pie is dark matter. So a colleague at the University of Chicago, Rocky Cole, in his talks, likes to say that you should not be, don't let the bright light fool you. The dark side controls the universe. Dark matter holds it together, so dark matter is what is responsible for the formation structure, but dark energy determines its destiny in the sense that its large-scale behavior is dictated by this dark energy. So let me comment first on dark energy, since it's the biggest piece of the pie. And so it's obviously a big open problem, but the interesting thing is that dark energy does have a pretty trivial solution. Okay, let me tell you why. So don't worry about understanding the meaning of that equation, which is actually a set of 10 different partial differential equations. These are called Einstein's equations, and these equations, or this set of equations, describes how matter and energy behaves under general relativity. So it's our best bet at how the universe behaves. So if you look at this equation, there's a term that naturally belongs to this T mu nu, the matter-energy tensor, and this term is called the cosmological constant. It has negative pressure, and the cosmological effect of this term is precisely what you need to explain the dark energy. And it's built in this equation in the form that looks like this, and this is a constant. This is Newton's gravitational constant, so it's also a constant. So it's simply a constant. It's a constant term that belongs to the equations, that we don't know the value of the constant a priori, but it should be there. And here's a picture of Einstein discussing this term. So dark energy has a trivial solution, the cosmological constant. It's definitely worth thinking about other models, but you should keep in mind that there exists a compelling and simple candidate, which is this cosmological constant that is built in Einstein's theory of relativity. Yes?
So did Einstein include the cosmological constant in his original equations, or was it a necessity to find exact solutions to them?
So Einstein did include it. You can find exact solutions without it. But the interesting thing is that when Einstein formulated general relativity, we didn't think that the universe was an expanding entity. We thought that the universe was static. And in fact, to produce a static solution to Einstein's equations, you do need a cosmological constant. Okay? So Einstein, it's not that he postulated, but he said, well, we should have a cosmological constant because the universe is static. Then Hubble came about with observations that instead showed that the universe was expanding. And Einstein said, well, that's okay. We just need to put 0 for the cosmological constant.
Wait, so when you say static, does that mean not changing over time?
Yeah.
Okay.
So with things essentially constant in time.
So acceleration is not static.
Acceleration is definitely not static, but even simple expansion with 0 acceleration is not static.
Okay.
Static is defined as not changing in time.
So no first derivative.
No first derivative or second derivative. So Einstein liked to say that cosmological constant was his biggest mistake, but it turns out that in fact today we think that the cosmological constant ought to be there to explain the accelerated expansion of the universe, which of course, as I said, was very recently discovered. Was awarded a Nobel Prize for just last year. So the history is cosmological constant was postulated to explain the static universe, then went away when Hubble discovered that the universe was expanding, and then came back when we discovered that the acceleration was not 0. Okay, so it's kind of ironic. Einstein was not wrong when postulated a non-zero cosmological constant. Now let me get to dark matter. Why is dark matter relevant? Well, if you just look at the matter content of the universe, dark matter is the lion's share. Okay, it's 85% of the matter content. So again, it's a huge open question, primarily because, as I will show you, there's no candidates for the particle making up the dark matter within the set of known particles in the standard model of particle physics. Okay, so it's an indication that there's something beyond the standard model of particle physics. So let me tell you 2 things about dark matter. First, why is this the qualitative picture? Why do we think that qualitatively there ought to be some dark matter? And second, why do we think we know the exact amount of dark matter in the universe? So why is this picture quantitatively the way we think it is? So I'm not going to belabor too much on the qualitative aspects, but let me just give you 3 instances. The first one is the observation of clusters of galaxies and the application of a theorem, a mathematical theorem known as the virial theorem. So let me tell you a little bit about this. So clusters of galaxies, which is, by the way, what my wife works on, are assemblies of tens to thousands of galaxies like the Milky Way, and they're the largest structures in the universe. So galaxies within clusters have some motion, so they move around, and they move around in the gravitational potential of the cluster. So you've got a bunch of galaxies, and they create the gravitational potential. These galaxies move around. Okay, so that's what clusters of galaxies are. The virial theorem tells you that in a system that is in equilibrium, you redistribute the kinetic energy and the potential energy in roughly equal amounts. So you end up in a system in equilibrium with particles that have roughly the same amount of kinetic energy as they do potential energy. You have potential energy. So by observing the velocities of galaxies within clusters, you can estimate the amount of mass that the cluster has. Okay? Just because the velocities of galaxies tell you about the gravitational potential. So back in the 1920s, Fritz Zwicky, who was a Swiss astronomer, pointed out that galaxies were moving a lot faster in clusters than they ought to be. And the explanation to this was that there was some extra matter in the clusters that was causing these galaxies to go faster than they should have, based on just the galaxies themselves. So this was actually the first hint of the existence of additional matter to stars and galaxies. Then on a more local level, we know something about the matter distribution in galaxies because we can observe rotation curves of regular enough galaxies. So if you have a galaxy like the Milky Way, I don't have much space here, but to make it do. So the Milky Way lies on a plane, okay, like this, and things go in circles in the Milky Way. So you can look at the velocity as a function of radius in things like the Milky Way, and you can imagine that this velocity is related to the force acting on particles of given radius. But the force is just gravity, so it just cares about the amount of mass that exists here inside the galaxy. So by observing the velocity of things rotating in spiral galaxies, we can infer the amount of matter in these galaxies. And what you get is that there's a lot more matter, there should be a lot more matter than what is observed, based on the distribution of velocity as a function of radius. Does that make sense, folks? Mm-hmm. Roughly? Okay. So this is the second instance that qualitatively there's something more than what we observe in galaxies. And lastly, and I think this is the most convincing argument, we would not have had enough time to form galaxies in the universe if dark matter were not there. And let me explain what I mean by that. So ordinary matter is charged. Okay, there's somebody interested in electromagnetism right there. So you've got two positive charges, and what happens to two positive charges?
They repel each other.
Yeah, they repel each other. So it's very hard for a bunch of protons to be put together and for them to form things like stars. Okay, so what happens in the universe is that at the beginning you've got a very uniform fluid with exactly the same density everywhere. But at some point, there's perturbations that arise, and these perturbations cause overdensities, places where you have a higher density than average. And these overdensities can, by gravity, overcome some of these repulsion. So eventually, even if you don't have dark matter, you do form stars. But because of repulsion of positive charges, this process is very slow. Dark matter is not charged. Okay, so you don't have any repulsive force. So when you have these density perturbations, you very rapidly create large amounts of dark matter, very large clumps of dark matter, and at that point you have very deep potential wells, and you overcome the repulsive forces of protons much quicker. We get a question.
So when you're talking about the repulsive forces of protons in stars, then is that the radiation pressure that you're talking about?
Basically, yes. Okay. So you've got a very high radiation pressure that is caused by repulsive forces. So in a sense, the pressure is the macroscopic manifestation of these repulsive forces.
So for a star to form, that pressure has to be approximately equal to the gravitational pull, correct?
Yeah, it has to be smaller than that because you want to have a, positive gradient of forces pulling stuff inwards to form stars, to start nuclear processes. So if you have dark matter, everything is much easier because dark matter is not charged, so it collapses much faster, and stars form fast enough to form galaxies within the time frame that we observe. So in other words, if there were no dark matter, stars would form much more slowly, and we would not observe the universe in the way we do today. We would not have galaxies, we would not have stars, we would not have planets. and so on. So this, I think, is the key argument. So we know the age of the universe, we know the time scales for the formation of stars. We wouldn't have had enough time for stars to form unless there was something that pulled particles together. So why is this the quantitative picture? So how do we know how much dark matter overall there is in the universe? And the answer to this is a budget question. So, in other words, we are going to do a subtraction of all of the matter minus the matter that is ordinary, okay, minus the protons in the universe. Okay, and the difference will give us the dark matter. So first of all, folks have studied very accurately the fluctuations of the cosmic microwave background, and here's the picture of the cosmic microwave background fluctuations in the sky. And if you look at the features of this cosmic microwave background, you will realize that the universe is not exactly flat, but it's very, very close to flat. And the relative height of these peaks, I'm not going to tell you precisely what these peaks are, but these peaks reflect the inhomogeneities in the universe of the cosmic microwave background. These heights here, the first and second peaks, gives you exactly a measure of the number of baryons in the universe, so the number of charged particles in the universe. When I say baryon, this is another Greek word that means heavy, and it indicates protons as opposed to electrons. Do you guys know what's the mass ratio between an electron and a proton?
Isn't it a 1 to approximately 1900 or 2000?
2000.
2000. Okay.
Yeah. So a proton is about 0.5 mega electron volts in mass, and a proton is about 1,000 mega electron volts. So the ratio is 1 to 2,000. So that's why baryons are associated with protons. There's of course many other baryons known to us, but primarily the universe is made of protons. And observations of the CMB tells us that it's only 4% of the matter content that is made of protons. And again, the name of the game here is measuring these peaks that quantify the fluctuations of the cosmic microwave background. There's a lot of cosmology that goes into this, but I have to be brief. Yes, there's a question.
So you said that to find the amount of dark matter, you do that entire subtraction thing.
Yeah.
But where do you come up with the amount of matter in the universe to start with?
Great question. 2 slides from here.
Okay.
All right. So there's another way in which we can tell how many baryons there are, and this way is by looking at very light elements, such as deuterium, proton and a neutron, lithium, helium-3, helium-4, and all of these abundances can be predicted as a function of the baryon density. Okay, so you've got a prediction as a function of the baryon density. You observe the actual densities of these elements, and when you find a match, you've got a number for the baryon density. Okay, so and again, this, in accordance with the CMB, tells you the baryons are 4%. Now the question is, how do I measure the total matter content of the universe? And here's the answer to that question. So usually cosmologists plot the dark energy versus total matter in a plane and show how different cosmological observations constrain this plane. So for example, you've got here BAO, which is baryon acoustic oscillations, and this is essentially a measure, a direct measure of the total matter content of the universe. Okay, these omegas indicate the matter content or the dark energy content divided by the total amount of matter energy in the universe. Okay, so BAO gives you this window here. These are supernovae, and supernovae essentially are standard candles that tell you how the expansion of the universe proceeds as a function of time, and it constrains the matter dark energy plane in this diagonal way, and then the CMB also constrains this plane to a sliver that is slightly above or below an exactly flat universe. So when you combine these two observations, you come up with this ellipsoidal area here that tells you how well we can tell how much matter there is and how much dark energy there is in the universe. But this is the total matter. Okay?